In this video, we're going to discuss simplifying radicals with variable radicands. It's very straightforward. You want to start by dividing the exponent on a variable by the index. The number of times it divides in is the exponent on the variable outside the radical, and the remainder is the exponent on the variable underneath the radical. So let's simplify the square root of x to the 7th. Even though there isn't an index shown here, I know that that's an index of 2. So let's divide 2 into 7. 2 goes into 7 3 times. So I'm going to have x to the 3rd outside of the radical. When we do that division, there's 1 left over, a remainder of 1. Therefore, we're going to have x to the 1st underneath the radical. Now, of course, we don't need to write that x to the 1st underneath the radical. We could just write the square root of x. I'm just trying to emphasize that that is where the remainder is. This is kind of a shortcut that I've outlined for you. Technically, we are using product rule. We're trying to figure out how many perfect squares live inside x to the 7th. So, for example, x to the 7th, I know that if the exponent and the index match, they're going to cancel out. So we want to figure out how many x squareds are inside x to the 7th. So this is the same as x squared times x squared times x squared times x. So the square root of x to the 7th is equal to the square root of x squared times x squared times x squared times x. And then product rule allows us to break that up into 4 radicals. And then we have a bunch of perfects, x times x times x, and then that square root of x underneath. And 3 x's multiplied together gives us x to the 3rd. So technically, that's what we're doing, and we see that we get the same answer. I just think it's a whole lot easier to simply divide the index into the exponent. The number of times it goes in, we have the variable to that power on the outside. The remainder, we have the variable to that power underneath. But understanding why we're doing those things helps us remember it. Let's simplify the 4th root of x to the 10th, y to the 5th. We're going to do the same technique of dividing. It's just we need to do it with the x, and then we also need to do it with the y. So I'll start with the x. 4 goes into 10 2 times. So that's going to give us x to the 2nd on the outside. There will, however, be a remainder of 2. So that's x to the 2nd underneath the radical. We'll do the same with the y. 4 goes into its exponent of 5 1 time, so that's y to the 1st on the outside, with a remainder of 1, that's y to the 1st underneath. This operation is multiplication here. Guess we could write it a little bit nicer. X squared y times the 4th root of x squared y. Just be careful when you're writing that your index doesn't end up looking like an exponent. Make sure you get it tight there in the crook of the radical. Now let's simplify some radicals that have both numbers and variables in the radicand. Since the way we approach simplifying numerical radicands is different than the way we approach variable radicands, I just say look at it separately. Product rule says that we can break it up into 2 different radicals as long as we have a product. So let's do that. Let's split this up into the square root of 16 times the square root of x to the 5th. We want to simplify the square root of 16. Well, that happens to be a perfect. So this is just 4. Now I'm going to divide my index of 2 into my exponent. 2 goes into 5 2 times, so that's x squared on the outside, and then we have a remainder of 1, so x to the first underneath. Let's clean out that outside. We have 4 times x squared, so let's just write it 4x squared times the square root of x. Next, we want to simplify the cube root of 250 a to the 7th, b to the 26th. Again, I'd separate the numerical radicand from the variable radicand. We want to simplify the cube root of 250. 250 is not a perfect, so we want to find the largest perfect cube that is a factor of 250. 125 works, so this is the same as the cube root of 125 times 2. So here we have the cube root of 125 times the cube root of 2. And we know the cube root of 125, it's a perfect. This is 5. And then we have the cube root of 2. But now we need to deal with these variables. I'm just going to bring it down so that it lines up when I do my division here. 3 goes into 7 2 times. So we're going to have a to the second on the outside. There's going to be a remainder of 1. So a to the first underneath. Now I'm going to divide 3 into 26. 3 goes into 26 8 times. So b to the 8th on the outside. We're going to have a remainder of 2. So that's b to the second underneath. And now we just want to clean this up. We're going to put everything that is outside of the radical, we're going to multiply those together outside, and then everything that's underneath the cube root, that's going to go underneath a single cube root. We get a final answer of 5a squared b to the 8th times the cube root of 2ab squared.